Welcome everyone to this exciting webinar on pathways to biohydrogen from biogas. As we transition towards a more sustainable future, clean and renewable energy sources are critical. Biohydrogen derived from the readily available biogas offers immense potential in this regard. Today, we delve into the fascinating world of biohydrogen production, exploring various pathways, challenges, and future directions. This webinar is brought to you by Bio360 Expo that will be held on 24th and 25th January in Nantes, France. Bio 360 Expo is an international exhibition attracting 5,000 participants from 45 countries, 450 exhibitors from more than 25 countries, and over 200 speakers from across the global bioenergy, bioeconomy, and CO2 removal sectors. In order to register, please visit bio360expo.com. Now, let me introduce our speakers for today, starting with Patrick Peters, CEO at Spark Clean Technology. Patrick has been working for more than 20 years in environment and energy, including biogas and water treatment. Next in line is Matti Malkamaki, Chairman at Hycamite TCD Technologies. Matti, a hydrogen business specialist and clean tech entrepreneur of over 20 years. Also with us today is David Farusenk. He's a CTO at MOF and research professor at CNRS. He got many prestigious awards, among them AICS Award and the Silver Award of CNRS. Now, all our speakers will give us a short introduction to their hydrogen-related activities, starting with Matti. Matti, please.
Yeah, okay, thanks, Anes. I hope you hear me well. So, as said, Matti Malkamäki is my name. I've been a clean tech entrepreneur now for more than 20 years and working with the biogas and or with the hydrogen for all this time. At Hycamite, what we are doing is that we are a methane splitting company so that we can split biogas at the moment that what we are getting from a local biogas site, and we are making ultra low or actually carbon negative hydrogen from that one, and then also high value carbon products, solid carbon products that we can sell to, for example, the electroconductive industry. I'm also quite active in the Finnish hydrogen cluster in Bothnia, which is a hydrogen initiative between Finland and Sweden, and also, for example, in the European Clean Hydrogen Alliance, where I'm second time nominated to be the CEO Roundtable member. Happy to meet you all.
Thank you. David, please.
Hello, everyone. So I'm David Farosen, a researcher, professor at CNRS. I'm coordinator of the Titan project, which is a European project on hydrogen production from biogas. So all the three projects are very related together. I think one of the main differences is that we are looking for new technologies with lower, I would say, TRL level, if you wish, so more fundamental and academic oriented, if you wish. And our concept is to produce hydrogen from biogas directly, so not from methane, but from the mixtures of methane and CO2, and to get a hydrogen-rich mixture that can be converted to fuel directly. So basically, our concept is to use catalytic steps that would overcome all the separation issues which are methane and CO2 on one hand, and hydrogen and methane on the other hand. So it's only catalytic steps from direct biogas to fuel. And so I will, I think, discuss on the technologies and partners in the question session.
Thank you very much. Patrick, it's your turn. We don't see you. Can you turn on the camera? Can you hear us, Patrick? Hello, hello. Okay, while we are waiting on Patrick, we will continue with our program. So, biohydrogen holds immense promise for the clean energy production, but several challenges need to be addressed. Throughout the webinar, our panel of experts will address some crucial questions and discuss the latest advancements in biohydrogen production pathways. We'll also have plenty of time for Q&A to explore specific concerns and delve deeper into the topic. Please send us your questions via messages on the platform you are watching us at, or directly to info@energynews.biz. So our first question goes to Matti. What are the most promising strategies for increasing biohydrogen yield?
I think that there are quite a few strategies for that one, but as we know that the biohydrogen, or in this case, hydrogen coming from biogas or biomethane sources, and I'm not talking now about e-methane, I mean, where we have green hydrogen and then the TCA solutions, but completely or directly from the biogas. The constraint that what we have in a biogas is that it is not possible to have that on the volumes that, for example, the industry is in need of. So we need to leverage that biogas with, for example, with natural gas, and still have negative carbon hydrogen available. And this is something that I for example, I'm pushing forward in our company, so that, or overall in the methane splitting industry, so that we can have these mixtures of natural gas and the biogas combined, and then have the use for industry in terms of negative carbon hydrogen. The other possibilities that we have, of course, is that how we can use the biogas directly, because quite often the biogas is available in a smaller quantities and in quite separated sites, so that we don't have access for those sites from the industry. And therefore, I think that what we need to do is that we need to have a little bit more technology development on hauling the biogas in a smaller volumes to industrial customers effectively and economically viable way. Those are just a few that come to my mind at the moment.
Thank you very much. And so now question for David. Integrating different technologies and optimizing various parameters.
Yes, as Matti said, the frame also we are working on is on the small biogas plants that would produce biogas in limited volume. And these biogas plants, if they want to convert into biohydrogen that would make a higher added value products, then I mean they could hardly afford any big investment. So the idea we have in mind is to have modular approaches, small conversion units, catalytic units that can be assembled together to go from biogas directly to fuel without any separations. And one of the key challenges is to convert the biogas. So it's about, let's say, a flow of mixtures of 2/3 of methane and 1/3 of CO2 into a rich hydrogen syngas mixture, while converting almost all methane and CO2. And this is a challenge because this reaction is what we said endothermic. It requires a high energy, and when you use a typical catalytic converter, the efficiency reduces very strongly as long you go to large scale. And we are developing microwave heating technology so that we can provide the heat directly to the catalyst and the reactor, which shall enable to reach about 100% or so of methane and CO2 conversion, making a stream very, I would say, appropriate for next process, next catalytic steps. So we intend to let's say integrate different catalytic steps, and with that we hope to get very high efficiency, process efficiency. Of course, we are still at the lab scale, and it has to be demonstrated at a greater scale, larger scale.
Thank you. And we have Patrick finally. Patrick, please give us a short introduction and we will go with your questions immediately.
Thank you. Sorry for the technical problem. Patrick Peters, I'm CEO and co-founder of Spark Cleantech. At Spark Cleantech, we work on new technology of plasmalysis to split methane into hydrogen and solid carbon. We have another possibilities to convert directly biogas into syngas. So that's the second option we have today. We are based in France, nearby Paris, and we are in industrialization phase with the pilots that will be deployed beginning of next year on a biogas plant in France. And the goal for us is to develop a modular plants to produce directly on site hydrogen and solid carbon to feed local usages, heavy mobility, etc. So that's it for my short presentation. Thanks.
So related to your technology, the question is splitting methane into hydrogen and solid carbon. Can you go into this a little bit deeper?
Yeah, in fact, it's plasmalysis technology we are developing. So it's an arc that will allow to put energy in the gas to split methane into solid carbon. So really decarbonize the methane and hydrogen. So it's quite a well-known technologies. There are quite maybe 30 projects worldwide working on that. What is specific to our technology is that we use what we call a cold plasma, or warm in English. It's kind of in between temperature. But the idea is to optimize the temperature of the reaction to optimize the need of electricity in the process. And that's a unique worldwide technology we are developing on this approach. And the goal for us is to really be able to approach 10 kilowatt hour of electricity per kilogram of H2 while doing this process.
Thank you. A question for Matti. What are the most promising technologies for separating hydrogen from biogas mixtures?
Well, this is I don't know whether I'm biased to answer this one, but of course I'm flagging out my company's own technology, so that when we are talking about methane splitting, whether that's methane pyrolysis or plasmolysis or splitting with a catalytic decomposition, that what we are doing, I think that those technologies are the most meaningful ones. We at HiCarbMind, we have been able to achieve very high level of energy efficiency, and also our carbon, that what we are getting out of the methane biogas in this case is high value. So we are producing carbon nanofibers instead of carbon black, and that gives us the secondary revenue stream in electroconductive polymers, electroconductive applications all over, and therefore this makes a really much sense, especially when we are coming back to the biogas production. Some of the produced hydrogen can be fed back into the biogas reactor, and there we do have a possibility for making the in situ methanation. That is, of course, still a little bit new technology on biogas production, but still that should raise the yield, that how much methane the biogas will include. So I'm really flagging for the biogas production or combination of the biogas production together with the methane splitting in that sense.
Thank you. Let's go back to David. Transitioning from lab scale to a commercial scale production.
Yes, of course. So this is the objective of the EU project Titan. So we want first to demonstrate at lab scale that we can convert the biogas directly at almost 100% yield to the syngas. And then when we have that, when we have found the catalyst, when we have found the process parameters, we will have to do a demonstration at 10 times the scale we do at the lab scale. And for that, as I said, we use microwave system. And so we have selected microwave technologies that are already at scale, that can be, I would say, put in parallel or in series, so that there is no new development to do. These microwave technologies from Muge or Leanfa exist. We use them, and the idea is to apply these technologies for biomethane, biogas cracking, so that the scale up will not be hampered by the technologies. So by the end of 2025, we will know whether or not we can apply microwave heating to biogas cracking in an efficient way, by providing metrics, cost like capex and opex. But as I say, the upscaling is a difficult task, and this is why we are supporting by European funding to take that risk.
Thank you. Patrick, carbon negative hydrogen and solid carbon for the net zero goal.
Yeah, indeed. People often say us that biomethane is already a green energy. So why working further on this type of methane? We really think we can increase the impact of the use of biomethane while producing hydrogen and carbon, both being products. As David said, I think it's really important to get value from both products in terms of economics and in terms of CO2 emissions, because you produce
Seems that Patrick has problems with internet. So we're going to Matti. Matti, what are the key economic drivers of biohydrogen production costs?
Well, first of all, biogas is more expensive than natural gas to produce with. It comes from the smaller units, and therefore usually there's no economies of scale that what you have in the fossil fuels and so forth. And also the biogas differs from the natural gas, for example, in that sense that natural gas is rather pumped from the earth than biogas that is being produced in anaerobic digesters. So we have this like a little bit like a disadvantage in the pricing to begin with. The good part on the biogas is that it is carbon negative or carbon neutral, so that we do have the benefit of that one being the CO2 friendly fuel, if you will. But then when we start to make hydrogen out of it, we will again add something on that production streamline that will add the cost. So overall, the cost for hydrogen that is being produced from the biogas will be a lot more than it is for the natural gas. I mentioned in the beginning that I think that for making the biogas really beneficial for the industry and also to help the economies of scale and the economics overall on the biogas is that it could be blended with natural gas, and therefore, because the methane splitting technologies are very low on their carbon footprint, so even a small percentage of added biogas into the feedstock will mean that the overall carbon footprint of that hydrogen will be more or less zero, or even slightly carbon negative. We have done a lot of calculations and estimations on our life cycle emissions with Haikamite. If you find from LinkedIn, my colleague Salla-Mari Marttinen has there announced or made some articles about the carbon footprint that would we have, and there you can see that actually the technology and the industries can benefit from this carbon negativeness. So I think that is perhaps the biggest way of helping the biogas or the biohydrogen to be able to enter the market, so that it's not used as a whole, but it is being used as a part of the solution. So I think that is perhaps the best way for leveraging it. On the other hand, we need to remember that what is the competing factory or competing, so to say, ecosystem that what we are talking about or fighting against or competing with, and that is the green hydrogen, of course. And now, when we have the green hydrogen prices that have been estimated for the central part of the Europe by 2030 on the levels of 6 euros per kilogram, and in Asia, for example, now even 12 euros per kilogram. So I think that we do have a possibility for biohydrogen to play there. But still, I would rather go for these industrial blended solutions rather than using the biogas as such. So that's how I see it. I don't know, David, if you have some other thoughts about this one, but.
Thank you. As for David, can process integration and optimization strategies be simplified for a large-scale production?
I would repeat a bit myself here on this question. This is, of course, a challenge in general for hydrogen production. Today, this is mostly methane reforming. So we take methane as a stranded gas or whatever, or from the wheel, mixed with water, heat very much, like 1000 degrees, and then we get the syngas that we have to convert again and to separate with amine technologies. We have to remove the CO2 from the hydrogen mixture. So it is again a series of catalytic and separation steps at large scale. And for the economics, the gas separation is a killer at low level, at small level. So you can do the economy of scale of CO2 capture in a big plant, but you can hardly do it in efficient way in a small plant like would be a biogas plant. This hydrogen purification or hydrogen separation is key in the economics, we believe, especially for small plants, especially biogas plants, and that's why I think we have to be, let's say, innovative or smart to try to circumvent these key issues of gas separation that are very energetically costly and which are also electric. Most of PSA, pressure shrink adsorption, separation, or membrane technologies require quite a high energy. And I think if we want to go to really low, energy cost solution, we have to be smart and try to integrate other technologies so that we can end up with a product, whatever it would be, hydrogen or electricity or e-fuel, to make it with a price affordable.
Thank you very much. We are going back to Patrick. Please continue where you stopped. I hope we will not have any other problems with.
Okay,
internet.
sorry for that. I had some technical issues, but I'm back. I think I was saying that carbon indeed is very important for economics, but also for CO2 emissions. When you produce hydrogen, you produce a decarbonized energy. When you produce a biocarbon and you use it, you replace current production of carbon, which are also highly emittive. So the impact is really great on CO2 emissions, and I really think using biomethane really increase the impact of the biomethane when we convert it into hydrogen and carbon. So that's what I wanted to say, and sorry for the little problem.
So just to continue on that one, is there a limitation on the solid carbon market?
Well, when you speak of the solid carbon market, the first type of market we speak of tires industry or rubber, that kind of stuff. Indeed, there's a limitation between 15-20 million ton a year. So it means 5-6 million ton per year of hydrogen. So there's the limitation, but I mean the market is here, and we can work today with no much problem. There are also other industries that need carbon for I don't know, for batteries, for inks, for etc. You have a lot of other usages that need to be addressed, and other bigger markets for biocarbon. When the idea is to avoid the emissions of users of other type of carbon that is burned, and here there is also a place to use biomethane to produce biocarbon and to avoid other emissions. So I don't see the carbon market as a limitation short term, and when we really think long term, I think there is also an opportunity to replace CO2 storage, captation and storage. And when you store carbon, it's much easier and safer than storing CO2. So our view long term is that we could store carbon instead of storing CO2.
Thank you, Matti. How can government policies and incentives promote the development of biohydrogen technologies?
Yeah, I think that the regulation is something that I want to speak a lot. So the regulation overall, if we have a look in different parts of the world, I mean, now we are in Europe, European companies that are being interviewed here, and in Europe the regulation is really very, very complex, and unfortunately it doesn't drive, on my opinion, towards the carbon neutrality or even to lower the carbon emissions. It's rather just driving to use some certain technologies, and that's it. If you have a look on the biogas, and especially when you combine that with the methane splitting, we, for example, have done LCA analysis on our plant, so that the hydrogen that would be can provide with a biogas coming from the biogas side can have a negative carbon footprint of minus 2.75 kilos. That's minus 2.75 kilos of CO2 equivalent per kilogram of hydrogen, I mean. And on the other hand, if you use green, well, or you produce green hydrogen, and you make the whole life cycle assessment for the green hydrogen, then if you use only the power coming from the wind mills, your hydrogen CO2 equivalent footprint can be something like 0.2 perhaps. But that would mean that you sacrifice your capacity factor quite a lot. And then when you add the grid power on it, you will actually have the positive emissions. I mean, really emissions coming from the green hydrogen in matter of 3.4 kilos, because that's a threshold that above that one you can't go. So why does not the European government include all the technologies that are technology neutral to the regulation, and just support something that is providing 3.4 kilos of CO2 equivalent emissions per kilogram of hydrogen instead of minus 2.75? This is a question that what we need to raise. So I think that when we are now starting this whole hydrogen revolution, if you will, there will be a lot of other technologies as well that are coming on the table, so that there will be photocatalyst and there will be this and that and so forth. From here to 2050, there's more than 25 years still to go, and within a quarter of a century, mankind is really good making new innovations for producing, for example, clean and low carbon hydrogen. So therefore, the regulation should be technology neutral and just driving towards the low emissions in this scale. And this is unfortunately something that the European Union is not very good at. I have been speaking, for example, last week in Canada to the government about the same stuff, and on a previous week with a congressman in USA, and they are seeing the world completely different way, so that they are seeing the regulation to be technology neutral and the lowest emissions to be the winners. And this is how they are very good on also accelerating their own technology, companies to conquer and to make and innovate new kind of technologies for this one. So coming back to this, that how we can accelerate or how we can help the government and the regulators to make better decisions, is that we need to provide them facts. We need to provide them life cycle emissions calculations. We need to provide them demonstrations that, okay, this is what we have been able to do, and this is like a good solution for the mankind, and this is good solution for the European Union, and this is good solution for everything. But these facts, they need to really be facts, and not like a populistic discussion in the forums where people that don't perhaps know the difference between power and energy can say that, okay, what we should do. Sorry for
Very
being
good
a little bit
point.
blunt here, but
Thank you.
This is my view.
So, David, what are the key challenges in transitioning from lab scale to commercial scale biohydrogen production?
So maybe, Arnes, I would like to continue the discussion that Matthias started. I'm on the price, and because as I say, I'm from the academics, I'm just starting here, but in our consortium, we as the European Biogas Association based in Brussels, and let's say the regulations are part of our radar, and looking at where are the limiting steps, whatever they are, technologic or in regulations, policymakers, and we have already identified indeed, like for example, one aspect that Matti has raised, that biohydrogen is not recognized in Europe yet, so to say. So basically, it would have the same value than hydrogen from oil, from fossil resources, and then we have to compete price-wise with that. So the difference has to be made somewhere else, and which makes it a bit more complex. Another aspect, of course, of this bias is the price of electricity, because in Europe, for example, we are not on the same page, all the countries in Germany or in France. So especially in France, so today I think we have one of the lowest because of nuclear power, but our government wants to push more the water electrolysis. So they are also here biased in the technology incentives, and at the end of the day, it's not obvious, as a Mattis, at all, whether the best CO2 lower emission technology will win, it would be possibly the one that has the best lobbyist, or that can find a trick between all the regulations. It's very I would say confused at the moment with the color of hydrogen. I think nobody understands the gray, the black, and the turquoise, and the white. And at the end of the day, that will be very difficult for our policy makers to make rules, regulations on that, and put a tag price on each colors of the hydrogen. So from my perspective, it's a bit far. Again, we are at lab scale, but already we do see strong hurdles if we want to convince the investors, whatever they are, to push I would say new technologies, because the future of the regulations is far to be clear.
Thank you. Patrick, I see you're smiling on this topic, so I assume you have something to add.
No, I mean, I fully agree with that. The French strategy has just been published a few days ago, and it opens the way for plasmalysis, pyrolysis, etc. systems, but only on biomass. I think it's also important to open to gas, to natural gas, and I will not spend 5 more minutes on that, but there's a very important topic on the regulation, and especially in Europe, and as Matti said, it's much more open in other continents.
Thank you very much, and we will now take just a short break and continue with the questions from our viewers. See you in a minute.
Introducing our revolutionary solution for companies and individuals who are looking for a way to achieve energy independence. Our cutting-edge installation is designed to transport and store hydrogen and its mixtures safely and effectively. This breakthrough technology will create local universal networks for the production, distribution, and consumption of hydrogen, offering a low-cost alternative energy source for the future. Our innovative system comprises vertically positioned tubular elements, connected together by another tubular element to form a tubular U-profile, which is placed underground. The upper end of one vertical tubular element is connected to the hydrogen supplier, while the other is connected to the consumer. This ensures automatic, instantaneous, and contactless transport of hydrogen from the producer to the consumer, creating a futuristic network of hydrogen pipeline connections. Our patented system offers many benefits, including reduced hydrogen prices for the end user, elimination of expensive road transport, the ability to use and revitalize existing disused mining wells, significant reductions in construction work and operating costs of hydrogen distribution stations, and does not require any labor. All of this is made possible by an innovative technology that uses well-known drilling and borehole horizontal techniques for the transport and storage of hydrogen. Our installation ensures safe and environmentally friendly storage of any excess energy without the loss of significant amounts of hydrogen in a highly concentrated state. We are also the only company in the world that offers a simple, fully scalar hydrogen storage unit for autonomous houses and buildings in the form of a U-tube. This solution is inexpensive, fully safe, and fully ecological thanks to the closed water circuit. Join the energy revolution today. Our system will help you achieve energy independence and contribute to a better, more sustainable future for all.
And we are back with the questions. So, first of all, we have salutes from Colombia and Ivory Coast. We have a lot of questions, so I think we will just take a few of them due to the time constraints. First one, what countries and regions are the biggest producers, and which regions have the potential to join in terms of resources and capacity? It's not directed question, so anyone can apply for it.
I can start if you want. I know.
Please.
Well, I think in Europe the growth of biomethane production is quite high. The goal is to multiply by 10 the production from now to 2030. We see, for example, in France, we went from 9 terawatt hour in 2022, and in 2023 it will be around 14. So the growth is very high, and I think the potential, at least in Europe, is huge. So I don't have much data on the other continents. So, but for Europe, for sure, there is a window to produce hydrogen and carbon from biomethane.
Thank you. Next question. What is the maturity level of the current pathways, and what is the outlook? What is the key challenge when it comes to scaling up? Maybe David?
It's not an obvious question because I would say the technology competes at different level. Some are very mature, so we know them well. We know their limits. We know their cost, and basically we know they cost too much. That's why we are looking for new technologies that in principle should provide solution at lower costs. And we start at lab scale, basically, more fundamental research. And then step by step, by upscaling, we get more data onto the real efficiency and real costs. And then we do an assessment at some point of the size, and then basically you have to go to industries, private partners, and try to convince them that it's a good solution or not. Well, they do the economics for you, basically, with the data you provide. And there are so many solutions. I think right now, maybe, or on the three panelists, there are three different technologies. Plasma, cold plasma, hot plasma, microwave, of course, electric heating, Joule effects, thermal. And each of them have their pros and cons technologically, and at the end of the day, you have to count how many the costs, investment costs, and energy cost, but also footprint and other life cycle analysis, and this makes the global assessment very difficult if you do not do it at the same level. And this is why it is very difficult to compare high mature technologies and low mature technologies together.
Thank you. How does the choice of pathway affect the overall efficiency of the biohydrogen production system? Matti?
Can you kindly repeat the question? I mean,
how does the choice of pathway affect the overall efficiency of the biohydrogen production system?
With the pathway, I think that they are responding, or the person that is making the question is referring to different technology, I would think. Well, as David said, so that we have different technologies, and even within this team, so that we have different kind of plasma or electro microwave heaters and then thermocatalytic stuff. I think that the biggest difference here in terms of talking about the different pathways is that how you compare the electrical efficiency of your production, and then also that what kind of carbon you are able to make out of this biomethane that you are producing. So the energy consumption refers quite heavily then to the carbon footprint of the hydrogen. So more energy you are needing there than the worse your carbon footprint is. And that, of course, affects to the price that what the customer is willing to pay for that biohydrogen, because they need to calculate their carbon footprint. And then, as what Patrick was also already mentioning, and there was this question about the carbon markets, that what kind of carbon markets can be served. So with the carbon black, you can serve some carbon markets, and with a graphitic or carbon nanotubes, you can serve other carbon markets, and the costs or the prices that you are able to get from these are very much different. So I don't think that there's just an easy answer that how to do it, but you need to have this whole holistic evaluation of the different technologies that you use.
Thank you. And Patrick, question for you. Is there a potential limitation on the market for solid carbon produced from the spark plasmolysis process, and how can its utilization be maximized for achieving net zero carbon goals?
Well, as I said earlier, there are some limitation on the market. I mean, but the potential is still huge. So I don't see short-term limitation on the market. And again, long-term view could be or our view is that we can store a part of the carbon we'll produce, and for that we'll need to produce very high quality carbon in the other end to be able to economically get good results in terms of cost of hydrogen, etc. So the goal long term could be to have a part with very high value and the parts that you can store, and the high value can pay for the storage and get rid of emissions due to this type of carbon. And that's the way we can achieve a good CO2 balance and get some negative footprint in the equation. Makes it possible to get net zero because if you only add the positive stuff in an equation, you will get a positive result.
Thank you. And for the end, please give me your last comments, starting with David.
Yes, to continue on the carbon storage issue in the Titan project, we have to do a study on the soil amendment in agriculture by the carbon Titan would produce. So we have the University of Hohenheim in Germany. They study a lot of different let's say aspects by mixing soil with the carbon we would produce, like for example whether the water would be more let's say viable when we mix the carbon, whether the plant growth would be faster, whether it would also trap some heavy metals. So we are looking at also a way to put again back carbon into the soil, because obviously when you use the biomass or the biogas, it was from the soil, and so it's kind of, let's say, recirculation back from the carbon to the carbon. We were let's say asking whether we, at the end of the day, such a biogas technology wouldn't deploy or remove too much carbon from the soil, and it's a way maybe also to close the loop. We have already first results that show improvement of the soil property at lab scale, and that depends on the nature of the carbon very much, whether it is amorphous or graphitic. And I think at the end it makes a lot of let's say fundamental research and understanding on also the bioorganism, how do they evolve, and this is, let's say, very, I would say, innovative science, not only for the methane but also for agriculture and biology, which makes sense basically.
Thank you. Matti?
Yeah, like a final statement. So I think that the biohydrogen as such has great potential for the future. I'm really very much for the thinking that we need to have all the tools that we have in our toolbox to be used. Biohydrogen is one of them. It is not like a silver bullet that will solve all the issues that what we have in this global challenge. But I think that it does. It should be given the possibilities that it has, so that it can really be part of the answer as well. I mentioned already that I'm for the technical neutrality, so that we should have the regulation to work for the hydrogen in that sense that actually the real emissions are the ones that count. And there also the biogas production or the biomethane production need to have a look also, for example, the fugitive emissions from the methane production and so forth, so that there's no such things that we are leaking methane into the atmosphere from the biogas plants as well. I mean, this is obvious, so that everybody has to do their fair share. As David already mentioned, also the carbon needs to be given its fair share of the regulation, in that sense that, for example, the use of the carbon particles, so that we use that as a soil improvement material, or we use that to replace part of the cement in the concrete elements or in tarmac and so forth. So this kind of possibilities we need to open. It's quite often asked from Hycamite team members that, okay, are you a hydrogen company or are you a carbon company? Because in the methane splitting, we always have these two products, and they both will do honor for this climate change, while tackling the climate change. And the last thing perhaps is so that we still have a long way to go, so that there's a lot of development that we need to do, and I think that there's a lot of possibilities that we will have. I already mentioned, for example, the in situ methanation, where I see some potential for the future, but we need to enable these different pathways for future development in the regulation as well. And I think that's how the biohydrogen should be treated from my point of view.
Thank you, Matti. Patrick.
Yeah, as a conclusion, I would say there are a lot of initiatives and companies working on this type of technology, using biomethane or methane to split into hydrogen, carbon. So let us work and be part of this decarbonization objective we all have, and I think we have a lot of promising technologies with plasmalysis or with what presented today, and will play a great role on CO2 emissions and on the transition. So yes, let us work. Let's speak to European politicians and the regulation. Let us work on that, because the impact will be great. And as it was said, we are working on two products, hydrogen, carbon, which makes a great difference on impact on the CO2, impact on the economics. So I think we are developing very promising technologies, and it will impact the way we are working today greatly. So that's what I wanted to say. And thank you, everybody.
Thank you, Patrick. So finally, as we conclude this webinar, it's clear that the biohydrogen from biogas holds immense potential for a sustainable energy future by addressing the challenges and capitalizing on advancements. We can unlock the potential of this clean energy source and contribute to a greener tomorrow. Thank you to our esteemed panel and all attendees for joining us today. Please continue the discussion on our online channels and share your thoughts, questions, and ideas on biohydrogen production. Once again, we are thanking our sponsor, Bio360 Expo, for the opportunity to discuss this topic. To register, please visit bio360expo.com. And that is all for today. Thank you again, and see you soon in the next one.